back to EC TechNest. In this lecture, we'll be discussing about the module 3 of VLSI design and testing. So the module 3 is all about CMOS process technology, and in this module it is mostly the theoretical questions that are asked in exams about the N-well and P-well process along with the twin tub process. So we'll discuss about one by one in detail. So the first one is silicon semiconductor technology. So silicon is the purest intrinsic state semiconductor with an electrical resistance that lies between that of a conductor and an insulator. Unlike metals whose conductivity is primarily due to free electrons, silicon's electrical property can be significantly modified by introducing the crystal lattice. So the process of adding impurities or atoms to silicon is called doping. The introduced atoms are known as dopants, and it can either donate free electrons or create the electron holes or vacancies. So further, the dopants are called acceptors, and example of acceptors would be boron and gallium, and the example for donors would be phosphorus and arsenic. The N-type and P-type silicon materials are brought together and transition region is formed, that is the PN junction. After that, we'll be discussing about the wafer processing. So semiconductor manufacturing begins with the silicon wafers, which consists of thin discs of single crystal silicon, typically 75 to 150 nanometer. Next, we'll be discussing about the Czochralski method. So wafers are cut from the ingots and grown using this method, that is the Czochralski method, and this technique is highly used for producing high purity silicon. So this is the Czochralski process for manufacturing silicon ingots. So this is the direction of pull. It has a seed as well as the crystal holder along with the heater, and this region is the growing crystal region along with shield, and the inner part is the quartz crucible with the graphite liner and also the molten silicon, and the down part is the crucible support to hold the device firmly. And next is high purity polycrystalline silicon is melted in this quartz crucible, and it is surrounded by graphite radiator and is heated using the radio frequency induction. So whenever the seed crystal is dipped into the melt and slowly withdrawn while rotating, the silicon solidifies and maintaining the single crystal structure of the seed. And next is wafer slicing and polishing. So the grown ingot is sliced into wafer using diamond tipped blades with a thickness of around 0.25 mm to 1 mm. At least one face is polished to a mirror finish to remove surface irregularities and also to ensure defect-free surface. After the wafer slicing and polishing, the next process would be oxidation. That is, the silicon dioxide plays a crucial role in the fabrication of silicon integrated circuits. Oxidation process is further classified into two types, such as dry oxidation and wet oxidation. In wet oxidation, we are using an oxidizing atmosphere containing water vapor and operating at 900 degrees Celsius to 1000 degrees Celsius, and wet oxidation provides faster oxidation rates, whereas in dry oxidation we use pure oxygen as the oxidizing agent with high temperature of 1200 degrees Celsius, and dry oxidation produces a denser and higher quality oxide layer. And the next step is oxide growth. So SiO2 has roughly twice the volume of the consumed silicon, and the effect is illustrated in the N-channel NMOS device. So this is the N-channel MOS device where the field oxide projects in both the direction. Next step is selective diffusion. In selective diffusion, we follow three steps, that is opening the window in an SiO2 layer along with removing the SiO2 layer selectively and using the etching technique. And the third step would be exposing the silicon to a controlled dopant source, and also to alter the electrical properties. The next process is photolithography and etching. So removal of SiO2 layer is achieved by using a process called photolithography, in which we are coating the wafer with the PR, which is called photosensitive resist, and exposing the PR to UV light uh, through a patterned mask. It develops the photolithography. So here you can see this is the silicon wafer on which SiO2 layer is deposited, and further the PR or the photoresist is formed. When it is exposed to the UV light on a glass mask, there are mask patterns that are formed here. After the process of etching, only certain part of the silicon wafer is exposed to the UV rays, and other part is covered with photoresist and silicon dioxide. Next process is electron beam lithography, in which it has emerged as more precise technique for achieving line width, and it is classified into direct patterning from digital data without mask, and it also has high flexibility, allowing different patterns in different wafer region. Next one, the conclusion would be EBL, that is the electron beam lithography, offers the highest resolution at the cost of speed and expense. Next we will be discussing about the silicon gate process. So it is used as an interconnect in integrated circuits and the gate electrode in MOS transistors. So steps involved in silicon gate process. First step is field oxide formation. A thick layer of SiO2 is grown over the wafer surface. This oxide is selectively etched in areas where the transistors will be placed. So this is the figure A represents field oxide formation. Next one is gate oxide growth. In gate oxide growth, a controlled layer of SiO2 called the gate oxide is grown on the exposed silicon surface. This serves as an insulating layer beneath the polysilicon gate. And the third step is polysilicon deposition. Here in figure C you can see this is the deposition of polysilicon on the surface of thin oxide and silicon substrate. And the fourth step is dopant diffusion. In dopant diffusion, the wafer is exposed to a dopant source, thereby leading to formation of two N+ regions and diffusion of impurities. And the fifth step is final processing, in which the structure is covered with SiO2 layer and contact holes are etched for the electrical connections. So in exam, if they ask the question, write the steps in silicon gate process, you have to explain each step in detail along with the diagram. We'll discuss about CMOS technologies such as the P-well process and the N-well process in the next lecture. Thank you.